Hello everyone, welcome back. In our previous video, we understood about the tree data structure and then understood the different types of trees using real life example. In this video, we will focus on tree traversal techniques. Before going into the details of each technique, let's first understand what is tree traversal means. Tree traversal means visiting all the nodes of the trees in specific order. Unlike arrays or linked lists, which are linear data structures, tree requires different traversal methods to efficiently explore all the nodes. If you see this tree as an example, one node of the tree can be connected to the multiple nodes. So it basically creates the multiple paths, and we need to visit all these paths efficiently to visit all the nodes of the trees. Let's understand the types of traversals. So there are mainly two traversal principles or techniques, depth first search and breadth first search, DFS and BFS. So these two techniques are mainly used for the data structures which are non-linear, like trees, graph, etc. In this video, we'll cover the subtypes for each of these traversal technique, DFS and BFS, for binary tree. Like in DFS, we will cover pre-order, in-order, and post-order traversal for binary trees. And in BFS, we will cover level order traversal type. Let's understand the depth first traversal or depth first search. DFS explores a tree by going as deep as possible along a branch before backtracking. So basically, we start from the root and explore one branch by going as deep as possible till the leaf. So it follows the root to leaf approach. And once that branch is visited, it backtracks and checks for the other branches. So as we can see here, it is basically visiting each branch one by one and backtracking and checking for another branches to visit so that it can visit all the nodes of the tree. So this is called as a DFS, basically going into as deep as possible by picking one branch and then exploring another branches. So for example, if you see maze, we start from the start point and try to reach till the end. If we start from one path and if we see that we are not able to reach to the destination, we backtrack, or basically we go back and check for the another path. Similarly, in a tree DFS traversal, we check for one branch till the end and then backtrack and check for the another branches which are reaching to the leaf node. Let's understand the subtype of DFS for binary tree, which is pre-order traversal. Pre-order traversal means that we visit the root first and then explore the left subtree and then finally right subtree. We follow this order for each node in a tree. Root left right. For example, when we start with the root 1, then we go for the left subtree for that node 1, which is 2. When we come to the node 2, we visit it and then we explore the left subtree of that node, continue till we hit the basically the leaf node. And once we visit the leaf node, we backtrack and check for the right subtree. We do this for each node in a tree, and once that particular left subtree is visited, we then backtrack and go for the another side, which is right subtree. So let's understand the implementation of pre-order traversal using a iterative approach. So if you see here, this is the class tree node, which is storing the value and left and right pointer for left child and right child. This is the function logic for iterative pre-order implementation. So if you observe one thing, that in a DFS, or basically in the subtypes of DFS, like in pre-order, we visit particular branch as deep as possible from starting from root to leaf, and then we backtrack to the previous node to check for other branches, right? So if we see here, we are basically need to keep track of the nodes visited and then come back to the previous visited node or backtrack to the previous visited node for checking other branches. So here we need a backtracking capability. So which data structure we can use to maintain this? So we had understood this part in our stack data structure video, that stack is useful in a case where we need to do backtracking. So we'll use the stack here. So this is the base case when the root is null, just return. And as discussed, because it requires backtracking, we are using the stack data structure. In a stack data structure, we will push the root node. Now this is the while loop, which is basically continue till there is any node present in a stack. So we first remove the node from the stack because we visit the node first. In a pre-order, we basically visit the node and then go to the left and then go to the right. So we pop that node from the stack, we print it, and then we check for the right child. If there is a right child, then push to the stack, and if there is a left child, then push to the stack. Why are we pushing the right child first here is because stack is last in first out. If you want to visit the left child first, then that left child should be put into the stack last so that it can be popped first. So now it will again come back to the beginning of the while loop. It will pop the node from stack, which is 2, and then print that node, which is 2. And then for 2, it will check whether there is any right child or left child. Yes, 5 and 4 are right and left child of 2. They are pushed to the stack. The execution will again come back to the beginning of the while loop. And it will pop the 4 from the stack. So we visited the 4. Then it will check for the right and left child. No child, then it will not push anything. Then it will again come back to the beginning of the while loop. It will pop the current node, which is at the top of the stack, which is 5. Visit that node, check for any right or left child. If not, then it will come back to the beginning of the while loop again and pop the 3 node, which is at the top of the stack. It will print that 3 node, and it will check if there is any right or left child. There are no right or left child for the node 3. So it will come back to the beginning of the while loop. Now stack is empty. So we came out of the while loop. So we saw how using a stack, we maintain or keep the track of nodes visited, and backtrack, basically pop the node from the stack, basically check for another branches. So this is the iterative implementation of pre-order binary tree traversal. Let's understand the in-order binary tree traversal, which is the subtype of DFS. Here for each node, we visit the left subtree for that node as a root, and then we visit the node and then visit the right subtree of that node as a root. So basically left, root, and right. Let's understand here. So basically we don't visit the node here. We go as deep as possible till the left subtree. Then we print the left subtree. We visit the node, basically the root, which is the for the subtree, which is 4. Then we go for the right subtree, which is null here. So it will backtrack. Then it will visit the node, which is 2. We'll check for the right subtree, yes. Then it will go to the right side. We'll print that node. It will then backtrack till 1, and for 1 it will check, it will visit the 1, which is the root, and then check for the right subtree of the 1, which is 3. We'll print the 3 because there are no left and right subtree for node 3. So this is the in-order traversal explanation. Let's understand the implementation of in-order binary traversal using iterative approach. So if you see here, in-order traversal function, we are using the stack because in DFS, as we understood in previous slides, we need to keep track of each node so that while going back, because we go from root to end and then we come back again or backtrack again for checking another branches. So for this backtracking purpose, we need to keep a track of nodes, and then we need to check the last visited node, for which we need to check the other branches. So because of this backtracking requirement, we need to use the stack in all the subtypes of DFS traversal. Like as we saw in the pre-order, in order also we are using the stack. So initially stack is initialized. Then we are maintaining the current pointer, which is pointing to the root, which is 1 here. Then in this while loop, if the current is not equal to null, or at least there is some element to traverse in a stack, we continue it. So because it is in order, we need to traverse the left subtree as deep as possible till we hit the null. So here in this while loop, we are continuing to visit the left child, which is basically we push the node 1 to the stack, then we go to the left of 1, which is 2, we push it to the stack, then we go to the left, which is 4, then we push it to stack, and then the current becomes null because the left child of 4 is null. Then it comes out of that while loop. It then pops the node because the in order is left, go as deep as possible, and then visit the node. Now we came till this left, and then now we are coming to visit the node. So we will pop the 4 from stack. We will basically now current will point to the 4. It will print that 4, and then it will move to the right subtree of that node 4. Now current will point to the null again because there is no right child of the 4. Now it will come back to the beginning of the while loop. Now current is null, so it will come back here and pop the, so it will basically backtrack. It will pop the node 2. Now the current is pointing to 2. Now for 2 it will go for the right subtree, which is 5. Now it will push the 5. It will go to the left of 5 again in the beginning of the while loop. Current is null. Now current is pointing to the null. So we printed the, we popped the node 5 from the stack, we printed it, and then we try to check for the right of the current. What is the right child of the current? 5 is null. So it will point to the null. Now current is null. So we cannot go into this left subtree logic. We'll pop the node from the stack, which is basically 1. We will print it, and then we will check is there any right subtree for that node. If yes, it is there, node 3 is there, so which we will push into the stack. Now we will go to the left, we will traverse the left subtree for 3, which is not there, it is null. Now we will pop the current node from the stack, which is basically the node 3. So current will point to the node 3. We will print it, and then we will try to go to the right subtree of the node 3, which is null. So now current is null and stack is also empty. It means that we visited all the nodes. So using the stack, we implemented the iterative solution for the Inorder traversal, where we traverse the left first, then pop the stack node as a visited node, and then go for the right subtree of that node. Let's understand the post-order implementation, which is the subtype of DFS again. So we'll use the stack also here. So what is post-order? We visit the left subtree first, then right subtree, and finally the root. So basically, we are visiting all the children of the node and then visiting the node. So in a DFS, basically, depth first search is that all the childs of the current node are visited first, or traversed first, and then we come back to or backtrack to that particular node, right? So let's understand the post order. So it will go into left side as deep as possible. Then for left side, it will check for node 4, is there any right? There is no right. Basically, it will then visit the 4. It will backtrack and come to the last node, which is 2. It will check, is there any right subtree? Yes. So it will come to the 5. It will check the left and right for 5, which is null. So it will print the 5. It will backtrack. Now for subtree with node 2 as a root, we already visited its child, left and right. So we will print the 2 node. Now it will backtrack to 1. For 1, now left subtree is visited, it is going to the right subtree. It will print the 3 because there are no left and right for 3. Then it will backtrack, and then finally it will print 1. So if you see that for each node, all of its childs are visited first, left, right, and then node. Let's understand the iterative implementation of post-order binary tree traversal. It is a subtype of DFS, so similar to other traversal types like Inorder and Preorder, where we need to keep track of nodes visited and backtrack to the previous nodes for checking another paths. We are using the stack in this post-order iterative implementation as well. So we created the stack, and we are maintaining the two variables current and last visited. Current is pointing to the root, last visited is equal to null. Why we are maintaining the last visited? We will understand that soon. So here you can see there is a while loop which will continue till current is at least pointing to some node or stack is not empty. So if the current is not null, it will basically push the current and go for the left, because in post order we visit the left subtree first. So it will push the current which is 1 and then go to the left which is 2. It will push the 2 and then go to the 4. It will push the 4, then the current will basically go to the left of 4 which is null. So it will not go into this if condition, it will go to the else condition. Now we will check the peak node. What is the peak node? Peak node is a 4. So peak node means the node which was visited, or basically the node which was traversed previously. And the peak node right is not equal to null, but the peak node which is 4, the right of that is null, and last visited is also null. So it will not go into this if condition, it will go to the else condition. Basically it will print that node and remove from the stack. The reason it is not going to this if condition, because the node 4 does not have a right subtree. So it popped that from stack and it printed. Now it will come back again to the beginning of the loop. Current is still pointing to the null, so it will go again into the else. Now the last visited is the node of 4. So 4 is the visited node which we have completed the traversal. So it will go again to the else part. It will check the stack, the peak basically, which is the node 4, 2. So it will basically check the peak node and whether that peak node has any right node. So 2 has a right node which is 5, and last visited node is a 4. So we have not visited the right subtree of this node 2. So we need to visit it. So the current will point to the 5 now, and it will come back to the beginning of the while loop again. Now for the 5, we'll push that 5 and it will go to the left of the 5 which is null, and then next time when it will come, it will go to the else part. It will basically check the top node which was basically we pushed to the stack, which is 5. Is there any right subtree for that node we need to visit? Now the right subtree for the node 5 is null, so it will not go to the if condition, it will go to the else. It will print the 5 and then it will update the last visited as node of 5. Now it will come back to the beginning of that while loop. So the current is still pointing to the null, so it will again come to the else condition. It will pop, it will basically check the peak node which is 2. Now the peak node is 2. Does it have any right node? Yes, which is 5. And did we visit that last that right node? So here we check the last visited node, which is node of 5. The reason why we are keeping this last visited is that if we don't maintain this last visited, it will again go and start the traversal for node 5, which will create the loop, right? That's why we maintain the last visited to check whether we have traversed the right subtree for that node or not. So for node 2, we have already traversed the right subtree, which is node 5, based on the last visited variable. So it will basically go to the else part and it will print that 2 and remove from the stack. So the last visited will be 2. So you can see for 2, all the children of 2 are printed before or visited before. Now the stack top is 1, current is still pointing at null, so it will go to the else condition. Now it will check the peak node which is 1. So now does 1 have a right subtree? Yes, it is 3. Did we visit it? No, because last visited is 2. So it will basically point the current to the peak node which is 1, right of the peak node which is now 3. Now current is pointing to 3. It will basically come back to the beginning of the loop, push the node 3 to the stack and go to the left. Current is now pointing to the null. Now then it will come back again, it will go to the else. So the peak node was 3. Does it have any right subtree? No. So it will go into the else condition. It will print that 3 and pop it from the stack. Now the last visited will be updated to the node of 3. Now current is null, so it will come back the beginning of the loop. Current is null, so it will go to the else condition. The peak node is 1 now. Now does it have a right subtree? Yes, which is 3. Did we visit it? How are we checking it? The last visited node. Last visited node is node of 3, or basically we already visited the subtree with the node 3 as a root. So the last visited is equal to peak node dot right, and it is visited, so we'll not go into the if condition to avoid that loop which we discussed. It will go into the else condition. It will remove that from the stack and print that node 1 and update the last visited node equal to 1. Now current is also null and stack is also empty. So this we will come out of this while loop. Now we understood the post order implementation using the iterative solution using stack data structure. Now let's understand the breadth first traversal, BFS. BFS is a tree or graph traversal technique where nodes are visited level by level before moving deeper into tree or graph. So basically, if we take this tree as an example, this tree will be divided into the levels. So the first node, root node is level 0. The child nodes are connected to that first root node will be in a level 1. So all the child nodes connected to the level 1 nodes will be coming to the level 2. So this tree, we can visualize how it is divided into different levels. So in a BFS, each level is visited first. So level 0 nodes will be visited first, and then level 1 nodes will be visited first, and then the level 2 nodes will be visited. So the level 0, then level 1, and then level 2. So if you see that the node which is coming to the top of the tree, or which are coming, which are getting uh, visited first, will be basically, or coming to the top of the tree will get visited first, like 1, then 2, 3, then 4, 5. So this actually gives us the idea that we can use the data structure which allows us to have first in first out characteristic, because the node which is coming first in a tree starting from level 0, they are visited first. So we can definitely use the queue as a data structure here. So let's understand the BFS with real life examples. So map. So when we see any location, right, we put the start location and destination. We can see multiple paths from that start location to destination. So basically it is checking all the immediate paths connected to it from start location. So this is nothing but a BFS. So let's understand the breadth first traversal BFS subtype level order traversal for binary tree. So if we see here the tree node, which is storing the integer value val, and left and right are the pointer for left child and right child. So this is the method which is basically the iterative implementation of level order. So in previous slide we understood why the queue data structure is used in iterative implementation of level order, because the node which is coming in early levels are visited first, and the nodes which are coming later are visited later. So it's kind of a first in first out characteristic which we can achieve using queue. Let's understand the root is null, so just return. So we are declaring the queue here. We add the root, which is 1. We enqueue it to the queue. Then in this while loop, we are traversing all the nodes till there is some node present in the queue. Now we dequeued the node 1 from the queue. We visited that node, printed that value, and then we basically check for all the childrens for that node. We can visit it in any order. Generally, we visit it from left to right. We can visit it from right to left also, depending on the problem. So we check, are there any childrens for that node? So we push all the childrens to the queue, like left, right, depending on the order or problem we are trying to solve. Here we are checking for the left to right. We are pushing left child first and then right child, so that we can visit the left child first, because queue is a first in first out. So it will again come back to the beginning of the while loop. It will pop or enqueue from the queue, dequeue from the queue, which is 2. Now current is 2, so it will print it, and then it will check for all the children of 2 and basically enqueue it to the queue. Now we will basically visit the next node, which is 3, and then print it and check for all the children for that node 3. We don't have any children for node 3. So we'll go for the next node, which is 4. We don't have any children for node 4. So we just again come back to the beginning of the while loop and dequeue the node 5, print it and check for any children's. We don't have any children's. So basically queue is now empty and we come out of that loop. So this is how the level order traversal is implemented using queue as an iterative approach. So we understood about the tree traversal, what exactly mean by tree traversal, the different techniques of tree traversal like DFS and BFS, and then we covered the subtypes in DFS and BFS which are specific to binary tree traversal like preorder, inorder, postorder in DFS, and level order in a BFS. We then understood the iterative implementation of each of this subtype traversal technique in detail. So hope you understood the explanation and got a fair idea about how the traversal techniques works for the binary tree to visit the nodes in specific order efficiently. If you like the video, please share and subscribe. Thank you so much.